Okay, now we know what is called entropy loss. Entropy loss. So now we can define the weighted average after split. Weighted loss, weighted average entropy after split. Is given by H after equals to SL plus SR SL multiply the H SL plus SR times H SR. Okay, and we just choose a split. That maximize the information gain. Information gain, which is defined by HS minus H after. So this is the information of the nodes in your parent node, and this is the split information in the two average of the entropy in the two splits. Okay, and we want to pick the split that maximize this information gain. Maybe let's see one more example here. Suppose now we have the initial parent node. We have the 20 cases labeled as C. Okay, and we have 10 samples labeled as D. Okay, so now the information of this HS is given by 20 negative 20 over 30 multiply the log 20 over 30 minus 10 over 30 times log 10 over 30, which equals to you can use calculator. You can calculate, it's approximately 9.918. And after you split, okay, suppose you have the split, and you cut your feature space. You can for this case we have the 10 cases labeled as class C, and we have the 9 cases labeled as labeled as D. Okay, on the right node, so this is R left, this is S left, this is SR. Okay, we have the 10 cases labeled as C, 1 cases labeled as D. Now we should use different color here. And then we can calculate the entropy on this case too, which gives you negative 10 over 19 over log 10 over 19 minus 9 over 19 times log 9 over 19, which gives you 0.998. Okay, and this SR you can calculate in similar way, negative 11 tenths log 10 over 11 minus 1 over 11 log 1 over 11, so which gives you 0.439. And then we just calculate, using these two numbers, we calculate the H after. Which gives you, remember H after is calculated by this way. So which is, so on the left hand side is 19 cases. It's 19 plus 11. It's 19 multiply 0.998 plus 11 multiply 0.439, which gives you 0.793. So okay, so for this new split we have lower cost, and the information gain will equals to HS minus H after, which equals to 0.125. So okay, so now we can see after the splitting our node, our tree will do better by 0.125. Actually, information gain will always be positive. Except when one node is 0, when empty, or we have the half-half case, okay? If or for the case we have the probability yi equals to c for all node in the left node equals to probability yi equal to c for all points in the right node, okay? So for example, in this case, if you calculate the gain for this split, you don't have any information gain, which means this is a bad split. It's a bad split. Maybe let me show you one more plot here. So this plot shows you the entropy function with respect to PC. Okay, as you can see, this entropy function is strictly concave. Strict concave means, suppose this is we have two splits here. We have split 1, split 2 here, and for example, for this case, right? This is SL, left node, right node. So suppose this is where the left node, the proportion is 0.5 something. And this is the node on the right hand side is also the proportion is PC. Okay, and the weighted average will be a point somewhere in the lay on the line connecting these 2 points, and this is strictly concave, which means this point will be always below than the entropy gain before the split. Okay, before the split. So because this entropy function is strictly concave, the interior of the line tangent is strictly below the curve. Any point on that segment represents a weighted average of the 2 entropies for suitable weights. If you unite the 2 sets into a one-parent set, the parent set's p-value pc is the weighted average of the children's nodes pc. Therefore, the point directly above that point is the curve represents, so this point represents parent's entropy. The information gain is the vertical distance between them. So this is the information gain. So the information gain is positive unless two child set was both have exact same PC. Okay. So suppose on that scenario, suppose you have 2 points on has same probabilities. Okay. Then the gain is 0. Okay, on the right hand side, this is a cost function of the using the cost with the misclassification percentage, which is the method 1. We say it's a bad method in this case. Okay, as we can see, this is not a strictly concave. So if we have the two child node here, if we draw a line segment connecting 2 points on the curve, the segment lies entirely on the curve. In that case, uniting two child set into one or splitting the parent set into two changes neither the total misclassification sample nor the weighted average of the percentage misclassified. So in that case, there's no information gain in this case. So in other words, this does not distinguish the quality of the different splits well. So now we have the cost function. We can minimize or we can maximize the information gain for each split. So now we need to find a way to choose a split. Although it seems like we have infinite many choices, but actually we always have only a finite number of the choices. For example, for a feature with binary features, value. Okay, for example, X could be the smoking status. Is a patient is smoking or not smoking. Okay. Then there is only one split, right? So just the 0 and 1. So that's for discrete case. So similarly, if the xi is a categorical value with more than 2 values, we just split using the number of the categories they have. Okay, and if the feature is quantitative, okay, so like the example we used at the beginning of the class, for example, the x is wind speed. So how do we find the split? For example, x is equal to the wind speed. But actually, it looks like we can have many choices, right? We can choose from there. Suppose the wind speed can maximum at 100 miles per hour. So we can choose as many cases as we can. But seems we have infinite many choice, but actually it's not. So what we do here, for this case, we sort. So this case, we sort all datas for example, suppose we only have few observations. We have the x1 is here, x1 I, suppose let's omit this index here. Suppose we only have few observations, data point x2, x5, x3, x4, okay? And we split between each pair. We split between each pair. Between each pair of unequal consecutive values. For example, if we sort suppose our data point, we only have four points, and actually you cutting from here or cutting here is same. So you just find a middle point, cutting the consecutive points in the between. So that's all the possible choices for the split. Actually, there is also an algorithm to calculate this entropy for each split. So here maybe I can give one example. Suppose we have a point x1 is here, x1 is here, x2 is here, x3, x4, x5, okay? And for this case, this is labeled as suppose this is labeled as, we have two labels. This is labeled as class C. This is labeled as class C, okay? And this is labeled not class C, maybe class D, class D, class D, class D, okay? And on the way we choose our splits, okay, we can calculate the entropy. For example, if we choose this one, there's a 0C, right? 0C. And on the right hand side is there 2C. And for this one, we have the 1D. On the right hand side, we have 2D. Okay. If we choose the split this way, okay, there's 1C here and 1C here on the right hand side. And there's 1D, 2D. Okay. So when we find the middle point of each cut, we can calculate how many labels on each side, and then we can calculate the entropy directly. Okay. So this is how the algorithm is implemented. And then we can find the split with maximum information gain and the computational cost. For this method is just O1 time, because it's linear. You just find the point linearly one time, you can calculate the entropy, and then you can find the split with the maximum entropy gain. Okay, I think that's all I want to talk about today about classification trees. In your lab, you can find some more Python code to implement this method.